All right, we're looking at oxidation numbers in 4.9 here. There are rules. The rules are pretty straightforward. Things that are elements, 0. If they're ions, follow the charge. Sum of oxidations, so that means that if the overall compound is a 0, the overall sum of the oxidation numbers must be 0. If it's -1, the sum of the oxidation numbers must be -1, or whatever the ion is. Groups 1 and 2 always will have a +1 and a +2. Remember, unlike ionic charges, which is an actual property of the ion, this is just a construct so we understand the relative positive and negative attractions of these. So oxidation numbers aren't real as opposed to a real property of an ionic charge. And we know charges are number, then positive or negative. Ionic states are negative and then the number. I know, chemistry always wants to make it more confusing than others. Now, in compounds, nonmetals are assigned in this order. So whatever's on top is going to trump whatever's on the bottom below it. Read through these rules. They're basically very straightforward. You just need to understand them and utilize them as we go throughout the year. So let's take a look at some examples here. Chromium, element, therefore 0. Chromium 3+, ion, therefore +3 would be its oxidation state. Now when we have CCl4, we take a look at that little table. So when we see here, we see that often it's the negative ions that really dictate these, while the hydrogen, except for in this case, it indicates the +1. Now chlorine, I don't see carbon on here, so chlorine is going to be our main focal point. Chlorine has a -1 oxidation state. There's 4 of those, so you have -4. That means carbon is going to have a +4 because the overall charge is 0. So 4 times -1, -4, carbon would have to be 4+. I look at my strontium and bromine. So strontium is a 2+ charge, and it's in group 2, so it's always going to be +2 for its oxidation state. Bromine, fitting our values down here because it's in group 7A, the halogens, 1- for each. Sulfur and oxygen. I see sulfur is further down than oxygen. Oxygen is going to have a -2 oxidation state. There's 3 of them, so -6. That means sulfur will have to be a +6 in this case. Over here, we have nitrogen and oxygen. I see oxygen is above nitrogen, so all the oxygens together will be -6. Since I have to have a negative in the end, that means nitrogen will have to be a +5. So +5 and -6, add those together, gives you -1. So utilizing these is key in understanding these relationships. It's similar to electronegativity with the exception of hydrogen, I'd say being the lone example. Be sure to get some practice and come back to these and ask questions and the rules when you need them. Now, oxidation reduction or redox reactions are very big in chemistry. Now, this is an introduction to them. So if you go online and start looking at redox reactions, you're going to find stuff way more complicated than you need to know now and throughout the rest of the year. So I'd really suggest that you focus on AP Classroom and me in order to really look at what you need to do for this section and for this course. You need to be able to identify what's being oxidized and what's being reduced, construct them, which essentially put them together, and then assemble. So remember, reduction is a decrease in the number. So if this oxidation state is +2, its charge is 2+, its oxidation state is +2, it's going to be reduced, goes from +2 to 0 because it's an element. Likewise, if we start off as an element and it becomes an ion, that's negative, it goes from 0 to -2 as its oxidation state. Electrons are always going to be incorporated with these because, again, that's how charges change. That's how a oxidation number would change. So a positive ion plus electrons gets you an element plus electrons gets you an anion. Oxidation is an increase in the number, so going from 0 to 2 plus by shedding the electrons. Or the idea of a -1 to a 0 by, again, shedding electrons. So just think about the redox rules to know, is it going up or going down? Remember, reduction is going down in charge, oxidation is up. But these are just like chemical reactions. All things need to balance on both sides, including electrons and total charge. Now, ignore the states of matter for now. They will make a difference, but that'll be in Unit 9. So let's just take some of these in action. All right. So if we get some of these that we start off, given these half reactions, you can see that this one is the oxidized because it goes up. This one goes from 1 to 0, it's reduced. Now, if we put these together, you end up seeing that, oh, I've got electrons on this side, electrons on this side. They need to be equal numbers. So if one was imbalanced, you need to multiply every coefficient by that number in order for it to balance. But in the end, you get rid of those electrons. You see you've got copper to copper, 2 silver to 2 silver. 2 plus 1 is 2 plus. 2 plus equal. Equal in number, equal in charge. Again, another example here. We can see that we already have some coefficients all set up. Even if we didn't, what you can easily do is multiply those so the electrons balance. If the electrons balance, then your charges are also likely to balance. I've got 4 aluminum, 6 oxygen, 3 times 2, 6 oxygen. Look at the charges, nothing over here. 4 times 3 plus is 12 plus. 6 plus 2 minus is 12 minus. Those will cancel out as well. Again, all we're doing is we're identifying which one's the oxidized and which one's the reduction and assembling. That's all I've ever seen when it comes to redox reactions. We don't need to look at it in an acidic form or a basic form. I think they've really simplified those over the years. So again, we have the electrons, those will go away. You're left with the iron and the copper and the iron. Charges are equal and opposite. All of these things will be canceling out for the electrons, and then again, assemble. Double check to make sure your ions are all good, and you should have very little issues with this type of section. And even when we get to the other parts, it becomes even simpler. Oxidize, reduction. Each half reaction is already balanced for the atoms. Same number of atoms on each side. Each half reaction is balanced for charge. They're already done. So when you put them together, they kind of cancel out, right? If this is 0 in total and that's 0 in total, 0 plus 0 is 0. You want to add them both algebraically, canceling the electrons. Never have electrons in the net ionic. And that's what these are. These are net ionic equations in the end. So get some practice. Let me know what questions you have. I'll catch you on the flip side.